let's discuss that.
Do I have to write anything, Professor?
No, Betsy, please take your seat, and I will do the writing.
Okay.
Thank you. First, I'm going to outline the key points of our subject. Then we will briefly discuss them and move on to phosphorus and metals removal. Is it okay with you?
Of course.
There are 4 items in total. Item 1. Rocks are the main reservoirs of phosphorus. The most common minerals containing phosphorus are phosphates with calcium. These are phosphorite, fluorapatite and hydroxyapatite. Less common minerals are phosphates, which contain iron and aluminum. So, Betsy, as we can see,
phosphorus is always bound to metals in the lithosphere.
However, apart from calcium, aluminum and iron, phosphorus is also bound to rare metals, such as strontium, lead, yttrium, scandium, ytterbium, uranium, etc. Item 2. Unlike nitrogen, phosphorus doesn't make toxic compounds in its natural cycle. Toxic phosphorus compounds
are man-made.
Exactly, but we will talk about that a bit later. Now, item 3. Less than 10% of phosphorus can be found dissolved in the hydro ecosystem. More than 90% remains in a bound state. It is part of the composition of the hydrobionts and can also be found in bottom sediments, which consist of organic detritus and insoluble phosphorus salts. And finally, item 4. Nonetheless, phosphates will dissolve in water ecosystems. But do you know under what conditions, Betsy?
Phosphates either dissolve in acidic water with pH below 6, or they dissolve in anaerobic zones.
Absolutely right. Let's summarize all of the above. Phosphorus always makes insoluble chemical compounds with metals in an organic environment. Therefore, by removing phosphorus from wastewater, it becomes free of various metals which may be toxic. And of course, Betsy, I have already prepared a problem related to our topic. Let's take, for example, a surface flow constructed wetland. What happens to the dissolved phosphates in this constructed wetland under the intense growth of biomass?
May I write on the board?
Of course you may, Miss Doolittle.
During the intense growth of a biomass, phosphates participate in 2 biochemical processes simultaneously. A smaller proportion of phosphate dissolved in water is assimilated by the growing biomass of plants. Furthermore, the growth of the green biomass makes the pH more alkaline and stimulates phosphate sedimentation. The change of pH in wetland water, along with intense plant photosynthesis, can be described by the following equation.
During photosynthesis, plants absorb dissolved carbon dioxide. The absorption of carbon dioxide by plants shifts the pH to a more alkaline state.
That's my answer, Professor.
Fantastic, Betsy. Now let's focus on our main subject. Please write down on the board, where do metals and phosphorus go? As we have already discovered, the greater part of phosphorus in a constructed wetland is not assimilated by plants, but rather falls into the sediment. Let's see what happens to deposited phosphorus salts. Can these sediments dissolve in the next biological processes, or does it remain unchanged? To answer this question, we have to consider the quantitative distribution of phosphorus into the basic elements of a wetlands construction. Betsy, do you remember the diagram of the distribution of phosphorus balance, which we analyzed in one of my lectures?
I remember that diagram quite well, Professor.
I'll take your word on it. Let's analyze this diagram without going into detail. So, phosphorus exists in 3 states simultaneously in any type of constructed wetland. Betsy, what are the 3 states?
First, the dissolved state. Second, phosphorus is assimilated by biocenosis, that is to say, by living and wilted plants, periphyton and plankton, which turn into organic detritus. Third,
phosphorus is contained in its mineral phase, namely in floccules, suspended particles, and bottom sediments.
Absolutely right. And now, Ms. Doolittle, could you please write down the data for the phosphorus content for each point you have just outlined?
In grams per square meter, sir.
Exactly. I'll dictate. Phosphorus in water, 1.25 grams per square meter. Living plants, above ground mass and roots, 7.5 grams per square meter. Wilted plants, 1.25. Periphyton, 0.15. Plankton and organic detritus, 0.01. Phlox, 0.25. Mineral suspended matter, 0.01. And finally, the bottom sediments, 60 grams per square meter. Betsy, have you got it down?
Yes?
Wonderful. Now, using this data, I'd like you to calculate first the total amount of phosphorus in each of the three phases: in the liquid phase, in the biocenosis phase, and in the mineral phase. And secondly, to calculate the percentage of this total.
I've got the answer.
Very quick.
It's not me, sir, it's my phone. The amount of phosphorus in the liquid phase is 1.8%. In the biocenosis phase, it's 12.6%. In the mineral phase, 85.6%.
Okay, thank you for then. Your calculation results show that the mineral phase holds the main share of phosphorus in the constructed wetland.
Yes, that's clear, Professor.
Therefore, I have a question for you. In which boundary zone of the constructed wetland, where phosphorus is in its mineral phase, does it change to its liquid phase more intensely?
Okay. Mineral phosphorus turns into liquid phosphorus or dissolved phosphorus in the upper layer adjacent to the boundary between water and sediment.
Right, Betsy, but could you explain your answer?
The thing is that the anaerobic conditions necessary for phosphate dissolution are developed in the near bottom layer next to the water. Am I right, Professor?
Yes, you're right, Ms. Doolittle. Your answer is correct as always. I would like to ask you some more questions, but first, we should discuss the basic technologies that stimulate accumulation of phosphorus in constructed wetlands. These technologies are based on the patterns of phosphorus phases transitions in
constructed wetlands.
Exactly, Ms. Doolittle. Could you be so kind to list these phases we have just covered?
The liquid phase, biocenosis phase, and mineral phase.
Interestingly, each of these phases is a two-way street. It means that depending on biochemical conditions, phosphorus transforms reversibly from one phase to another without any point of no return. Here I want to emphasize that only in constructed wetlands, as opposed to activated sludge systems, phosphorus can constantly change phases. Similarly to the rule of communicating vessels. Betsy, in your opinion, what must a constructed wetland do with all of this phosphorus?
The constructed wetland has a clear but difficult task. It has to remove the phosphorus from water as effectively as possible.
For these purposes, we have technologies which can lock phosphorus in undissolved phases. Let's have a closer look at three of them. The first technology. The plants selected for a constructed wetland are ones that have the capacity to considerably increase their biomass within a short period of time. However, it should be noted that the time of intense phytomass growth is limited. It takes 3 to 5 years in different types of constructed wetlands. After this time, a natural balance is established. The amount of growing phytomass becomes almost equal to the amount of dying phytomass. To solve this problem, without reducing the efficiency of phosphorus removal into the assimilating phytomass, the upper part of the plant biomass is removed in some wetlands. Thus, as the above-ground phytomass grows, phosphorus removal through the assimilation does not slow down. The second technology is embedded in the very construction of the wetland and is based on the fact that the intensity of phosphorus sorption is directly proportional to the specific surface area of the wetland substrate. And finally, the third technology, which stimulates chemical reactions, triggering the sedimentation of phosphorus compounds. Usually iron or calcium compounds are used as such stimulants. When added in the wetland substrate, they release cations of these metals into the water. Phosphates are accumulated in organomineral deposits so that the effluent comes out free of phosphorus. Thus, the cycle of phosphorus in the constructed wetland is completed, isn't it, Miss Doolittle?
Yes, it is, sir.
No, Betsy. I skipped one point intentionally for you to correct me. As I have already said, phosphorus transformation is bidirectional. To conclude our topic, it's important to point out that precipitated phosphorus eventually, once again, gradually dissolves, with one part incorporating into the plant biomass so that it can be removed from the constructed wetland along with this biomass. The other part, once again, undergoes sedimentation, thereby continuing the cycle. That's how we will conclude this topic.
I'm sorry, Professor. I didn't think it through.
Never mind, Betsy. As I promised, I have prepared a problem for you, and I am sure that you will solve it brilliantly. Betsy, is it possible for a plant's biomass to assimilate all of the phosphorus coming into the constructed wetland? Take your time to think it over.
My answer is the following. Certainly, wetland phytomeres can't assimilate all the inflowing phosphorus because, according to the Redfield ratio, to assimilate 1 atom of phosphorus, plants require 16 atoms of nitrogen, while…
Excuse me, Miss Doolittle. Could you specify what the Redfield ratio is?
The Redfield ratio establishes the proportions between atoms of carbon, nitrogen, and phosphorus in any biomass as 106 to 16 to 1 respectively. Since plants take carbon directly from the atmosphere and not from wastewater, we can exclude carbon from this proportion. Plants only take nitrogen and phosphorus from influence, but only in the proportion of 16 to 1 respectively. However, the amount of nitrogen in wastewater varies from 6 to 10 atoms per 1 atom of phosphorus.
Thus, to assimilate 1 atom of phosphorus, on average, wetland plants require twice as much nitrogen atoms. As a result, there is always excess of phosphorus in the wetland.
A perfect answer, as always.
Thank you, Professor. Our next topic is constructed wetlands within the landscape.
Yes, Betsy. And this topic is very important and of special interest for us as wastewater treatment specialists. But, as always, we have to approach it gradually. For a start, let's clarify how wastewater is commonly collected and how its composition changed in the modern world. There are 2 methods of wastewater collection. The first method is conventional one, and the second method is… Let's talk about it next time. I'm running late as always.
Professor, did you enjoy the play yesterday? I mean Pygmalion by Bernard Shaw.
No, it was mediocre.
And how were the actors?
Also mediocre. See you tomorrow, Miss Doolittle.
No surprise, you are impossible to please. The first method is conventional, the second one is the correct one.